Okay, we're going to try some Chapter 8 You Try It problems. The first problems that I put on here are a little bit easier, and then as we go into this, they get harder and harder. Realize if I cover hard problems with you, you learn a lot more from them. So don't get discouraged if you're finding them very hard. Just realize that if you struggle through it with me, you're going to learn a lot more. So what is the product of the following reaction? Which one of these down here, or which ones, would be the product of this reaction? So if I look at this problem, you will see that we're adding hydrobromic acid to 1 butene. The hydrogen will get added to this end carbon to make a secondary carbocation, and then bromide would add on here. And at first glance, he would say, oh, well, this is it. But if I look, this is also one of those compounds. So both of these are the correct answer. Which product results from the following reaction? Well, if I look at this, remember that this is just a solvent. That's dichloromethane. It does not participate in the reaction, so we would exclude this as one of the possible products. Then we know that chlorine adds across double bonds. So here is where the 2 chlorines are going to add. And so any one of these, this one, or this one, has 2 chlorines added across the double bond. But if I look, this one is missing the methyl groups that are here. See, there's no methyl groups. So it's either going to be this one or this one. It can't be this one because chlorines are going to have to add 1, 2, 1, 2, 1, 2, and these are 1, 3. So we can exclude that one and this one. So now it's either this one or it's this one. Which one do we see formed? This is syn addition. The chlorines are on the same side. And this is anti-addition. Chlorines on the opposite side. Chlorines and bromines add anti across double bonds. So this is my product of this reaction. Which of the compounds here result from the reaction of bromine and water in DMSO with 1-methylcyclopentene? If I look at this, DMSO is just a solvent. So I'm really having bromine and water add across the double bond. If I look, 1-methylcyclopentene, all of these have a methyl group and a cyclopentane ring. The rest of them, all of them have that. The rest of the molecule has to be a bromine and a hydroxyl group. So now I just have to go and look at each of these to see which one has the bromine and water, bromine and hydroxyl group added appropriately. What are the conditions for addition of bromine and water across a double bond? We remember that they have to be anti, and we remember that it's Markovnikov addition for the alcohol portion of the addition. So 1-methylcyclopentene, the more substituted carbon is where the methyl is going to be. So I have to look for a hydroxyl group where the methyl is. And if I look, the bromine, this would be on the bromine's on the more substituted carbon, so that is not Markovnikov for the alcohol. This is not Markovnikov for the alcohol. But notice the hydroxyl group is on the carbon with the methyl group, so it's Markovnikov for the alcohol group here, and Markovnikov for the alkyl group here. So these two are possibilities. Then I look at this one and I see that the alcohol is on the less substituted carbon. This one I can discard for another reason, because the bromine and the alcohol are on the same carbon. Remember, when we have bromine and the alcohol add across a double bond, the bromine ends up on one carbon and the alcohol on the other. So we can discard this right away because they're on the same carbon. So if I look at these two, I look to see what is the difference between these. On this, I see the alcohol and the bromine are on the same side, and in this one, they're on the opposite sides. This one is a result of anti-addition, and this one is a result of syn addition. So if I look at bromine and water, I know that bromine and water add anti across the double bond, so this will be the correct answer. So which compound here would be the best starting material to end up with this product? Well, if I look at this, the reaction that's ongoing is we're having hydrogenation over a palladium catalyst. What do I think of when I think of adding hydrogen across a double bond? I think, oh yeah, that's syn addition. And if I look at this molecule right here, I can see the hydrogens are both on the same side. Immediately, I can throw this out because I know the hydrogens are on opposite sides. What about the rest of these? Well, first of all, this benzene ring right here is going to be very hard to reduce with this condition. Remember that when you see benzene rings, they don't act as double bonds. They're highly unreactive. So hydrogen over palladium catalyst does not usually reduce an aromatic ring, so we can throw that out. If I look at this, hydrogenation is going to be over these two carbons. And so I can come in from this side or I can come in from the other side, and what we would find is we would get a mix of a cis and trans for the two hydrogens on these two carbons. If I look at these two molecules, you would have exactly the same thing. You could have hydrogenation on this side and hydrogenation from underneath, giving you both the cis and the trans compound up here. However, if I look at this molecule right here, hydrogenation across this double bond would put the two hydrogens on the same side. And so this is going to be your product. Okay, let's go through the answers here that are given. These are not double bonds. This is an aromatic ring, which is exceptionally stable and not reduced under these conditions. This is the only one that would give cis-decalin. This is the compound right here. What is the major product of the following reaction? Well, if I look at the chemicals here, the chemicals here are going to give you a diol. And if I look at how the reaction occurs, it's going to give you syn addition. So first of all, I can automatically look at this and say it must be a 1,2 diol. Here's a 1,2 diol, and here's a 1,2 diol. This and this and this don't fit those descriptions. So if I look at this, you can see the hydroxyl groups are going to be, if I add two alcohols across this is going to do syn addition of the two alcohol groups. This would be the result of syn addition. This would be the result of anti-addition. So what's the correct product here? That one is. Which of the following will react with periodic acid to give an aldehyde? The first thing you have to do is say, what does periodic acid do? Periodic acid will react with 1,2 diols. So right off the bat, you can say this one, and this one are not going to react with periodic acid. Why? Because they're not 1,2 diols. This is not a diol. This is a 1,3 diol, and this is a 1,1 diol, or a geminal diol. We want a vicinal diol, which is 1,2 and 1,2. So it's going to be one of these two. Now, let's look to see which one will give an aldehyde. When periodic acid reacts with a diol, it cleaves it and puts a double bond oxygen on each of the alcohol groups. So if I look at this and cleave this, it would put a double bond oxygen here and a double bond oxygen here. What else is going to be there? Well, since the carbon bond is gone and there's 2 bonds to oxygen and then to this, what must be left there? A hydrogen here and a hydrogen here. if it cleaves this, this is cut here and it puts a double bond oxygen here and a double bond oxygen here. What do we get as a product of this? There'd be carbon, carbon double bonded to oxygen, and then carbon. This actually would be a ketone. And this, because there's a carbon on either side of that carbon-oxygen double bond here, also would be a ketone. So this is not a product that will give an aldehyde. It gives two ketones. What does this do? When this cleaves, it's going to put a double bond oxygen here and leave that hydrogen that was there. Put a double bond oxygen here and leave the hydrogen that was there. See, each of these two carbons have one hydrogen on them. A carbon, an oxygen, and a hydrogen. A carbon, an oxygen, and a hydrogen. So when cleavage occurs here, it makes a double bond oxygen and leaves that hydrogen behind, and that is an aldehyde. It actually makes two aldehydes here. Okay, what are the steps to prepare 1-bromo 2-chloropropanyl, that's this compound, from 1-bromo propane, which is this compound? There's going to be more than one step. So on this problem, what you need to do is think, what do I need to have to get this? And then how can I use this to get there? So it's basically a think backwards and a think forwards problem. Try to do this problem. You may find it hard, but try to do this problem. Okay, if I do this problem, the first thing I'm going to do is say I need to have an alkene on here. So what I'm going to do is I'm going to go to a pen and write for you, if I can get it there. Okay, so I'm going to draw the product that I'm going to need to have. Notice you're going to have a double bond right in here in order to get this. What is that alkene? That is going to be this alkene. Okay. Okay, so I take that off, those two things off, and I get an alkene. How can I get from there to there? To get from there to there, I need to have chlorine and water. Okay, so to get there, I need chlorine and water. How can I take this compound and go to here? Well, we learned how to do that in the formation of the alkenes. What do I need? I need strong base. What strong base could I use? Potassium hydroxide would be totally acceptable. So I take 1-bromo propane and treat it with potassium hydroxide. So what would be the product of this reaction? The product of this, the reagents that I would need to do this reaction. Well, what's given here is sodium hydroxide, same thing as potassium hydroxide. Okay, so just now what we're going to do is try to prepare chlorine and water that I would need to get that from 1,2-dimethylcyclopropanol. How can I do that? Again, it's a thinking forwards, thinking backwards. In order to get to this compound, what alkene would I need? In order to get from this to that alkene, what conditions would I need? Okay, to do this product, the first thing I would need to see is what can I do to get here? Okay, at this point in time, you've learned that diketones can come from alkenes. What alkene would I need it to be? Notice it's 1, 2, 3, 4, 5 carbons. So I'm going to put 5 carbons down in a ring. Those 5 carbons have to be these two right here. This one, and this one have to be connected by a double bond. So I'm going to put a double bond in there. What else is connected? There's a methyl group here and a methyl group here. So I got to put those methyl groups on. Notice I just put them on. Okay, how can I get from here to here? Well, there's a couple ways we can do it, but one way that works quite well is to first treat with ozone. And then what's the next step? The next step is to treat with zinc and acid. So there's my zinc. Sorry about the messy handwriting, but this is real hard to write with a mouse. And hydrochloric acid would work quite fine. Okay, so that would take this alkene to this diketone. Now what I need to do is to figure out how do I get from there to here. Well, I have learned in the beginning of this chapter that I can take alcohols and make them into alkenes, and they make the most substituted dialkene, which would put the double bond right in here. Okay, what reagent do I need? Well, concentrated sulfuric acid works quite well, so we can put that one down. And there's what I would need to have in order to go from here to here. So what would you write down as the conditions that you can use to prepare this diketone from 1,2-dimethylcyclopropanol? Here it is. Sulfuric acid, ozone, zinc, and acid. There really should be a 3 in front of the zinc and acid as a third step. But still, you get the right idea. To treat cyclohexene or 1-methylcyclohexene, 2-hydrobromic acid. Hint, think about what is the stability of the intermediate, because the more stable the intermediate, the faster the reaction is going to go. Methylcyclohexene, 1-methylcyclohexene. Let's draw that compound for you so you can see it, just in case you're having trouble visualizing it. 1-methylcyclohexene, okay, will form a tertiary carbocation. Here's the tertiary carbocation. Okay, when you treat it with hydrobromic acid. And that forms faster than a secondary carbocation. This is cyclohexene. And when it is treated with hydrobromic acid, what happens? What is its intermediate? It is this intermediate. And this intermediate is secondary. This intermediate is secondary. And this intermediate will give only a single stereoisomer of 1,3-dimethylcyclohydrobromic acid when hydrogenated with hydrogen over something like palladium. All of these compounds are going to give 1,3-dimethylcyclopentane. If I look at this, because hydrogenation can occur on the same side as this methyl up as on the other side, and here again it can occur on the same side as the methyl group or on the opposite side. All of these will give you both the cis and the trans, 1,3-dimethyl, both of these will give you the cis and the trans dimethylcyclopentane. However, this one, because it doesn't matter which side hydrogenation occurs on, the methyl groups are not going to change their orientation, which is cis. This compound is going to be the only one that gives you one compound, one stereoisomer after hydrogenation. There's a compound X that when reacted with ozone followed by zinc and acid give these two compounds. What is compound X? Okay, when I go to figure this out, this problem, there's two ways you can approach this. You can go and you can take each one of these compounds and figure out what would be the product of ozone followed by zinc and acid. Or I can take these two compounds and try to fit them together to figure out what is the product. That to me it's faster to do it that way. And I'll show you how to do that way, but then I will also show you the other way. Okay, to figure out how to piece these two together to figure out what compound X is, I think, well, there's two compounds, so it can't be a symmetrical compound that was that underwent ozonolysis. So what I'm going to do is try to put these two compounds together in one compound. Notice this one's symmetrical, this one is not. What I'm going to do is, I know that the alkenes, when an alkene is treated with ozone, it's cut in half, and basically oxygens are put on the ends of the double bond. So what I'm going to do is I'm going to cut this here, and I'm going to cut this here to reverse that oxygen being put on the end of the double bond. Then what I'm going to do is I'm going to take this and I'm going to move it over and attach it onto this part of the compound, the upper part. So this is gone, I say to myself, and this is gone. What I'm going to do is attach this to this. And do you see, when I do that, I see that I get this. That's that top part over here. That's this part going over there. And then I'm going to take this part right here that has on the right, and I'm going to put it over here on the bottom. So that would be like this. And there's that methyl. See, there's a hydrogen here. And there's a hydrogen over here. And there's a hydrogen over here. But do you see how I'm placing the two halves of the compounds together and reversing that ozonolysis? So if I look down here, I can find that compound. There's going to be, it's not looking exactly oriented this way. Let me change back to the laser pointer. It doesn't look exactly like this. It's going to be turned a little bit. But what you want to find is a 6-membered ring with two alkenes that are 1, 2, 3, 4. So it's 1,4 cyclohexadiene with a methyl on the number 2 carbon. So I look over here and I see none of these all don't fit. Of these two, only this is 1,4. So this is the correct compound. And that is my correct answer. However, how can I test this out? I can go and I can test this and say, what would be the product of this compound? So I'm going to the number 2 compound, and I'm going to draw the product of ozonolysis from the number 2 compound. It would be this. Very messy drawing, isn't it? Okay, that, and then this ketone. And of course, there's hydrogens over here that we draw. Okay, what about this one? Well, I'm going to cut this one and this one. This is actually going to make 3 compounds, and this is going to be acetaldehyde. Okay, and then what is this going to be? That's going to be oxalic, well, some kind of dialdehyde. What is this called? I can't remember the name of this dialdehyde. Okay, this dialdehyde. Okay, and what's this going to be? This is going to be acetone over here. It's going to look like this. Okay, and none of these right now fit anything that's up there. Let's go ahead and look at this one. This is going to cut here and here. What do we get? Well, first of all, we're going to get formaldehyde from the left-hand part of the molecule. What are we going to get from this part of the molecule? It's going to be a ring-open compound, and it's going to be 2 aldehydes. But they're all going to be connected together. Okay, and there's going to be a ketone on there from this part of the molecule. Oh, wow, that's a lot of drawing. Okay, how is this? This is going to be cut here and here. So what do we get? We're going to get, again, 3 compounds, formaldehyde way down here on the bottom from that 1 carbon part of the double bond. Okay, what do I get up here? I get this compound. And this. I sure hope you can read these things. And then what about this part of the compound? Okay, I'm getting this. Very messy, sorry. Now, all right, which monomer here
can see how this
will
is all,
give you the polymer
shown below.
This is the only one that will give you the right
to
do this. Again, we see we've got 1, 2 carbons, 1, 2 here, 1, 2. If I want to look at what would be a monomer in here, this would be one of the monomers. This would be one of the monomers. And this would be one of, you see the repeating units? That's how you figure out by looking for repeating units. And you can see here, that is my monomer. It has to have been that there were double bonds here. And that this is the bond that's been eliminated. Okay, so I look for a compound like that. It's going to be a chlorine on a 1, 2, 3. Here, let me go back to the pointer. It's a chlorine that's on a 1, 2, 3 carbon compound. So I'm going to look for, and it's the carbon's going to be in the middle of the middle of the 3 carbon chain, and I'm going to have one side of it be a double bond. This is the only compound that will fit this. The rest of them, see here, if I connect these up, you would have the chlorine and the methyls on different carbon. Here too. Here you've got too many compounds. There's too many carbons. There's 4 carbons. Here you have too many carbons, 4 carbons. So this is the correct product for figuring out which monomer would give the polymer shown below. What is the product of this reaction? Well, the product of this reaction, either to figure this out, what you have to do is think, what does this make? This makes a carbenoid. What is it? It is going to be the carbenoid that has 2 hydrogens attached. So when that adds to this alkene, it's going to make a cyclopropane. That cyclopropane ring is, because this is a carbenoid that has only 2 hydrogens attached, it will just be a plain cyclopropane ring, and this is the product. Which of the following reactions would not yield at least 1 alcohol functional group? Okay, when I look at this, hydroboration of an alkene would put an alcohol group on an alkene. It would replace the carbon double bond with the addition of water. Here, when we use bromine and water, what happens is across the double bond we put a bromine and an alcohol group. So this would give us an alcohol group. If I use osmonium tetroxide, what happens is I make a diol with an alkene after it's reduced by sodium bisulfite. So this would make a diol, and so we have at least 1 alcohol functional group. Oxymercuration and demercuration, which is done with sodium borohydride, this gives us the equivalent of adding water across the double bond. But if I look at oxidative cleavage of an alkene, what would I get there? What I would get is 2 carbon-oxygen double bonds. This would not give an alcohol group. So that is the correct answer. Which of the following compounds would yield a trialkylborane that looks like this when you treat the alkene with borane and THF? Okay, if I look at this, I can see that there used to be a double bond in this. Where did the double bond have to be? Well, the double bond would have to be on this and this carbon. If I look at that, that means this was a 4-carbon alkene with a methyl group on it. And it has to be that that double bond had to be on the number 1 carbon. So, if I go down here and I look, I can see right off the bat, I can say it was not 2-methylpropene. I can also see it was not pentene because pentene would be a 5-carbon chain. And I've got a methyl group there. So I look at these 3 here and I see that there is but-1-ene or 1-butene and there's 2-butene. It can't be a 2-butene because that would put the boron on the number 2 carbon or on the number 3 carbon. The only way you can get a boron on a number 1 carbon is to have a number 1 alkene. So it's either 1 or 3. If this was an ene right here, the methyl group is on the number 2 carbon. So the only way we can get this adduct is to have 2-methyl-but-1-ene. What is the product of 1-methylcyclohexene with mercuric acetate and water, followed by sodium borohydride that has deuterium instead of the hydrogen? Okay, if I recall, what does oxymercuration do is it puts an alcohol on the more substituted carbon. So that would have to be where the 1-methyl is. So if I look, it's going to have to be, I'm going to have to eliminate this compound, and these 2 compounds, because both of those are putting the alcohol on the less substituted carbon. Next, I look at these 3, and I think about the addition, oxymercuration. It's going to put an alcohol group on the more substituted carbon and a deuterium on the less substituted carbon. This does not give us a addition of an alcohol and a deuterium across a double bond because a double bond have to be on adjacent carbons. So I can eliminate this one. If I go and I look at these 2 things, I see there's 2 deuteriums here. 2 deuteriums cannot occur. It has to be only 1 deuterium. And if I look at this, this is an alcohol on the more substituted carbon and then a deuterium on the other end of the double bond. This is the correct product. Which reaction sequence on an alkene will accomplish the same result as treating the alkene with ozonolysis followed by zinc and acid? Well, ozonolysis and zinc and acid will give a dicarbonyl product, and it won't matter what type of alkene you have, whether it's tetrasubstituted or disubstituted. If there's a hydrogen on the carbon double bond, the ozonolysis still gives you just a carbonyl and no oxidation down to a carboxylic acid. So let's go ahead and look and see which one of these would give you a dicarbonyl regardless of what's there. If I look at an alkene being treated with a peroxy acid, I would get an epoxide, and then treating it with potassium permanganate would just do oxidative cleavage anyhow, and what we would end up getting is a oxidation down to the lowest possible thing. So this is not going to give it to you. Not only that, you haven't seen an epoxide being treated with potassium permanganate, so you can just toss that out because I'm not going to give you unfamiliar reactions to consider. Right here, borane followed by osmonium oxide would do nothing. This would give you an alcohol. Osmonium oxide is going to want to react with an alkene, and it's gone by the time you treat it with this, so we can toss that out. Osmonium oxide will react with an alkene and give you a diol, and then the periodic acid will give you oxidative cleavage. So this and this up here, ozonolysis and zinc and acid, would give you the same result. If I look at treating it with the conditions for oxymercuration, then followed by potassium hydroxide, you would get an alcohol added across it would be oxymercuration would add water across the double bond and give you an alcohol, but potassium hydroxide is going to do nothing to the alcohol. Bromine and water followed by potassium hydroxide would give you, and then followed by acid. Wow, if the best that you could get from that would be a diol, because the potassium hydroxide could remove hydrobromic acid from this compound, but it's kind of a crazy way to go about things. And it would not give you oxidative cleavage, which is what ozonolysis does. So the only answer to this problem is number 3.